Okay, we are live? Maybe. Wow, that was fast. Way to go, YouTube. So we're still going to wait a couple minutes just to let people roll on in before we get started with this talk. For those of you who are here watching, thank you for being here. You're here for the Women in Solar Physics talk with Shadia Habbal. A very exciting moment for all of us here at the Office for Astronomy Outreach, but in particular me. So we'll just wait a couple minutes just to let people come on and roll in. In the meantime, Shadia, you are in Hawaii right now, in Honolulu. Do you want to tell us what the weather is like there?
Well, yes, it was very, very humid the past 2 weeks, and all of a sudden this evening it all cleared, and it's just delightful. So
That's wonderful. We are here in Tokyo at the Office for
yeah.
Astronomy Outreach, and it's hot, and very humid, very sticky. Yeah, summer in Tokyo is not nice. But yeah, my recollection of it's maybe like a 2-week period in Honolulu. Is that right? When it's
Yes, it's
very
very
unpleasant.
yeah, yeah.
And the
And
rest of the time it's
in
perfect.
August, yes.
Yeah. Okay, well, I guess let's get started. And we can just hope that people will join us as they come in. So hello, everyone. My name is Kelly Lumenthal. I'm the director of the Office for Astronomy Outreach, which is an office of the International Astronomical Union. We're based at the National Astronomical Observatory of Japan in Mitaka in Tokyo. I am here with two of my colleagues, Cynthia Duran and Naomi Asaber Fimpong, and we are here to warmly welcome Dr. Shadia Habbal to give this talk, the next in our series for the Women in Solar Physics. For those of you who are new to this series, we are doing this in honor of the 2025 Solar Maximum, and honoring all of the women who have spent their lives studying the sun and helping us understand our nearest star. So I want to tell you a little bit about Dr. Shadia Habbal. She is very near and dear to my heart. She is a professor at the Institute for Astronomy at the University of Hawaii in Manoa, which is where I did my PhD. And so for the last many years, she's been a personal, professional, and just overall mentor for me. And I'm really, really excited to have her here to talk to you about all the work that she's been doing for her entire career. So Shadia is a pioneer in studying the outer atmosphere of the sun. So that's the corona and that expansion of the corona into interplanetary space, which is the solar wind. And she's best known for her work that leverages using total solar eclipses as seen on Earth to study the outer atmosphere of the sun in ways that weren't achieved with other methods. So she established this group called the Solar Wind Sherpas, which she'll tell you about in a little bit. And that's the largest international collaboration that carries out these observations. And with this team, she's made really groundbreaking discoveries that have changed the way that we understand the sun and the way that the sun impacts the infrastructures that we have on Earth and the satellites around the Earth. So with that, I am going to get quiet and let Dr. Habbal take the reins here. So please go ahead and share your screen. And thank you so much for being here.
Oh, you're welcome. Well, I don't know how to start this. For some people, it's good evening. For some, it's good morning or good day. But anyway, it's an honor and a pleasure for me to be here with you and to have this opportunity to share with you some of the exciting time in my life, which I have spent basically observing the sun during total solar eclipses. I didn't start my career in solar physics this way, but I will tell you how it happened as I go along. So this background picture shows it's a gorgeous one that was taken in Chile in 2019 by my two colleagues, Professor Dirk Miller and Peter Annual. And you can see the eclipse sun in the sky, and the sky darkened, and how the whole landscape is basically dark. So it's an incredible moment to witness. even if you're not a scientist, as a human being, it's one of these really life-changing experiences. So on a normal day, let's say if you have a hazy day and the sun is about setting, you might see an orangey ball in the sky. But then, once upon a time, humans witnessed the brief disappearance of the sun with a strange halo around it. And for the Chinese, it was considered as a frightful, abnormal event, and perhaps caused by a dragon devouring the sun. Now, what's really interesting is there were some tablets in Ugarit that date back to 1223 BC, where they recorded, it's probably the oldest record of a verifiable solar eclipse. And in the 2nd century BC, there was also a tablet that established that the Babylonians actually were able to predict the 18-year cycle of eclipses. Now, eclipses happen, total solar eclipses happen once every 12 to 18 months, and they happen all over the world. So it's really remarkable that these people were able to discover these things. So it's not just the Chinese who were fearful of eclipses. For example, I found this in an article by Hayakawa. He has these two pictures from the King of France, Louis XIV, who was terrified by the eclipse of 1706, which was during the War of the Spanish Succession. So you can see, and other wars also were stopped because of a total solar eclipse, and the two fighting factions ended up deciding that they better have a truce. So, and then the fear started to turn into curiosity and observation. So this is a funny depiction of the servants prostrating and hoping that no ominous event will happen in association with the eclipse, while the scientist was looking through his telescope to see what was going on in the sky. So what did people see during the disappearance of the sun, as we call it? Because this is when the moon comes in front of the sun and blocks it totally. It just so happens, and it's a fortuitous coincidence, that the apparent size of the moon is the same as the sun at the distance of the moon. Now, because of the orbit of the moon around the Earth and the Earth around the sun, you can have a total blockage of the disk of the sun, the very bright one, by the moon. And it's only during these fleeting moments that you can actually see the corona. So before photography, people used to, scientists were engaged early on in the curiosity of observing this very unusual event. And the way they would do it is they had to draw what they were seeing. So here are two kind of outstanding examples. The one on the left was by Temple from 1860, where the arrow is pointing to something a little bit unusual. So everything is, most of the drawings show these rays, very, very filamentary structures, and this is what the eye sees. And in addition, you see these strange protrusion into the corona, which we call prominences. Here it was drawn in red because that's how they appear to the eye. This drawing was obtained about 18 years later, and I will talk about the phases of the sun. So you can see that they're very different, but what they have in common is that you see this very, very filamentary or fuzzy nature of the corona. And the black circle is basically the moon that's totally blocking the sun. Now, if you have any tiny part of the sun that is not covered, you will not see the corona. The corona's intensity is about the same as the full moon, and you can see stars and planets appear at the same during totality. With the advent of photography, people started to use photographic plates, and their cameras were huge compared to what we use these days. This is a silver print from a negative taken in 1889, and the one on the right is from 1893. Now, if you notice, there's a big difference between these photographic plates and these naked eye observations that were drawn. And it's only with and the reason being the eye has a huge dynamic range. And to get to that very filamentary structure, you need to take different exposure times and co-add them in a very careful manner to get really what the closest to what the eye can see. Now, what was interesting also, in Maunder published a book about, it's called The Indian Eclipse. And in this book, he made a compilation of observations taken prior to that year by both from sketches and also photography. I know it's very difficult to see what's the fine print, and I didn't have time to rewrite them in a larger font. But what he did is he found that there was some kind of a category, or the shape of the corona changed as a function of time. And he called this one at maximum, and this one after maximum, at minimum, and then after minimum. Now here's something, I guess there's a drawing that was missing, but he wanted to have the same number of frames in this picture. So what you can see here is the corona is never the same. It changes in an aspect, and I will show you in this talk how even at, for example, all these are at maximum, but they don't look the same. And I'll tell you what they mean by maximum. So I need to go back and talk about magnetism, the solar cycle. So before people observed the sun, the Chinese have a very, very long record of observing the sun. Galileo even observed it. And from the motion of the sunspots across the solar disk, he recognized that the sun was actually rotating. So in this, so from all the observations, people they counted, so these black blemishes on the surface of the sun, it wasn't known what they were. So they just had all kinds of theories. But they started to count how many sunspots were on the surface of the sun on a given day. And this compilation here is a modern one, and it shows you that it goes back to 1600. And you can see that during this period, there was what's called a Maunder minimum, because Maunder was the one who brought it to the attention to the scientific community. But then if you look past it, look at the blue ones, you see that every about 11 to 12 years, the number of sunspots goes up and reaches a maximum and then goes down. Not all maxima have the same maximum number. So for example, here you see the maximum is like 100 in 1820 something, whereas earlier in 1775, the numbers were close to 350. So the sun has this cycle on its own. And the question was, what is causing this cycle? So we have to go back to observations of the solar disk. And George Ellery Hale was an avid solar observer, and he had his own observatory. And what he noticed is that, of course, this is a modern picture of a sunspot, but even in his own time, these very strange like filaments extending from outside the darkest part reminded him of iron filings when you have a magnet. And at the time, Zeeman had discovered the Zeeman effect, whereby if you have a gas that's that's emitting light, and you put a magnet close to it, then you, instead of having just one spectral line, it splits into three. And from the separation here, you can calculate how strong the magnetic field is. So Hale decided to do the same. So he pointed the slit of his spectrometer at his sunspots with his telescope, and lo and behold, he found this pattern here where the line split. And he had a series of observations, and the average value of the magnetic field was several thousands of Gauss, and that's pretty high. And that was a major discovery because it was the first to notify the scientific community that the sun is a magnetic, has its own, it's creating its own magnetism. Now we know the Earth has a magnetic field, but nobody expected the sun to have a magnetic field. And I will show you throughout this talk how the magnetism is really defining everything in the corona. This is a more modern rendition of the change in the corona as a function of solar cycle, and it's taken from our own observations, just starting from 2017. I just wanted to focus on like half a cycle where you go from practically a solar minimum to a solar maximum. And so you can see that here the shape of the corona varies a lot from one time to another. And also, you can see the very fine filamentary structure of the corona, which we achieve through, thanks to my colleague, Miloslav Druckmüller in the Czech Republic, who has an incredible technique to process the images to bring out all the filamentary structures. And you can see that there are some very strange things. And if you remember the picture from Temple, he had something very similar to this one. And nowadays we know that they're due to large explosions from the sun, which we call coronal mass ejections. And in 2023, there was a fainter one further away from the sun. So they appear at different times, at different distances from the sun, or sometimes starting at the sun and so on. And then you have cases where you have this like almost waves propagating away from the sun. Now, the other very important discovery that was made during a total solar eclipse, and that was in 1869, was so the first one is the discovery of magnetism in sunspots on the sun. This one is during a total solar eclipse. So what Harkness and Young independently discovered, of course, this is again a modern rendition of the same type of measurement. They had a slitless spectrometer. So basically they just have you have like a grating and you don't have a slit, and then you reproduce the inner part of the corona in different, so basically the corona showed up in different colors. Now, H alpha, which is from hydrogen, was known. Helium at the time, I forgot if it was discovered before the other ones, but anyway, helium was also discovered during eclipse. And then you have another helium line here. And then there was this green line. And they didn't know, they could tell what the wavelength was, but they didn't know, they couldn't attribute it to anything they knew at the time. And it took about 70 years before Adlin and Grotrian came up. They were atomic physicists, and they came up with the discovery that this was the element iron that had been ionized to such a high level that it had lost 13 electrons. So for atomic physicists and astrophysicists, what they so for any ionized element, the Roman numerals refer to the number of electrons that are lost +1, because for hydrogen, which is not ionized, we just refer to it as H1. So that's why iron 14 is the 13 plus. So it's lost 13 electrons, so it's positively charged. And the only way you can get this iron is if the medium is at 2 million degrees. So here was the hugest, huge discovery. The surface of the sun is about 6,000, and all of a sudden you're seeing something in the corona that's at 2 million. And this is a big puzzle that most solar physicists are trying to find out what is really causing this sudden increase in the temperature. So the consequences from this discovery were manifold. So first of all, as I said, the corona was hotter than the solar surface. It's fully ionized. So there are plenty of free electrons. And so not very much longer, in 1958, Parker showed through a rather simple theoretical model that the corona at this temperature cannot stay bound to the sun. Basically, this gas is not bound gravitationally to the sun, but it expands supersonically. And he called this expansion the solar wind. And in 1963, it was the beginning of the space age, where both the US and Russia were competing to reach space and for space exploration. It was actually the US spacecraft that was the first that was launched outside, close to the orbit of Mercury, and they discovered this stream of particles, which are the solar wind, with different speeds. And it was basically a proton detector. So that was the beginning of the space age. So given with this hot temperature, that means the corona is actually can emit light in X-rays in very short wavelengths, in ultraviolet and gamma rays. Therefore, you didn't have to wait for a total solar eclipse, because in these wavelengths, you can see the sun itself, your corona, projected onto the solar surface. But you have to go to space, because you cannot have X-rays. They don't penetrate the Earth's atmosphere. So this is an artist rendition of the solar wind. It's basically, it creates an uninterrupted path leading from the sun to our planet. And it does impact the Earth's magnetic environment. It doesn't impact us directly. It's only through, when you have a very, very strong push on this magnetic shield, that sometimes you can get what we call a geomagnetic storm. I won't go into it today because I don't have time, but you might have heard about it. Now, so it's true that the corona can be observed in X-rays and ultraviolet, but there was a problem. And the problem was that from space, so Leo was a French observer, avid eclipse observer of the corona, and he got frustrated from having to wait so long to observe the corona and so on. So he came up with an optical design whereby you can put a blocker in front of your telescope and create an artificial eclipse. Now, it's true, but the problem is from the ground, you never succeed to bring down the brightness of the sky the same way you do during a total solar eclipse. So from space, it's a much more successful approach or enterprise. But the problem is, because you have for technical purposes, your occulter has to be much larger than the sun. Otherwise, you have some diffraction patterns at the edges. So the first very successful that's still operating is called the LASCO C2 coronagraph. It's operating from space, but you have this huge gap. So this is the size of the sun. And then you're missing something. In the extreme ultraviolet, you can actually see the sun, the corona projected onto the surface of the sun, because the photosphere doesn't emit in X-rays, so you can see the corona. Now, so what you put the two together, they're both from space and they're observing continuously, so you can't beat that. But the problem is you have this gap. So you don't know when something starts here, and then how does it connect to what you're seeing in the coronagraph? So this critical missing information, or this critical gap, is found to be only filled by total solar eclipse observations. So these images were taken at the same time as the total solar eclipse of 2012. And you can see it's only with the eclipse that you can make a connection between what starts at the sun and expands into interplanetary space. You can see here that you really have no clue. And whatever your wildest guesses are, you would never be able to think about something like this expanding from the corona or streamers in this fashion. So this is when my eclipse addiction started. So at the time, I was doing modeling of the corona and the solar wind, because we wanted to understand what was causing the solar wind to have different speeds, where was it originating from at the sun? So then it occurred to me that the only way to do it is to actually take advantage of a total solar eclipse to be able to image this transition, from the surface outwards. Now, I think I really had no idea about instrumentation. I just had the scientific idea. And I think somehow my upbringing and my background really were instrumental on me embarking on such an addiction, so to speak. So I come from a family of we're four girls, and our parents were very encouraged us. They basically let us do what we wanted, but education was really the most essential thing in the lives of women. And my mother, I think, is one of the most intrepid people I know, and I probably got my courage to do the things like this from her. Um, so, so where do the eclipses happen? Well, I started with the first eclipse was in India. It's this red one here. It was in 1995, and the duration was 42 seconds. It's probably the shortest eclipse I have ever witnessed, but it was one of the most beautiful. So there were five of us, and we only had two cameras, and we trained and I'll explain the type of observations we did a little bit later on. So we trained a lot to be ready, to have everything working and so on. So I thought, well, it's a one-shot deal. We'll take these images and that's it. Well, it wasn't a one-shot deal because I soon discovered that we needed to do better, and it became literally like an addiction. You want to see the next one, and you want to keep on take advantage of the advancement in technology, because when you launch a payload in space, you're stuck with the same technology and the cameras for like at least 5 to 10 years, if not much longer. With the eclipses, you can change your instruments when new technologies, for example, for detectors or cameras or filters become available. So, so after the second eclipse, one of my colleagues we were sitting around a campfire, and she said, we really need a name for our team. And I thought, well, what started it all was I wanted to explore the origins of the solar wind. And we were always traveling with big backpacks, carrying all our optical equipment in the backpack and checking the mounts. So I came up with the name, the Solar Wind Sherpas, and it has stuck with us. We started with a group of 5, and now we're about 30 people. All the people who have joined me have joined just because they really wanted to. It's not a financially rewarding endeavor whatsoever. Everybody puts in extra time over with their jobs, but it's something that has driven its commitment and love of the science and love of the adventure. So far, I have led 20 total solar eclipse expeditions, and the 20th was last year in 2024. Now, unfortunately, our biggest worry or threat is clouds. And when somebody asked me, well, how many eclipses did you lose to clouds? I started to count, and I was horrified to see that we lost 40% of them. So since 2015, we started to try to have more than one observing site along the path of totality, just to maximize our chances of observing total solar eclipses. So this is, I thought it would be fun just to show you what people did in the past. For example, this is from 1905. The telescopes were huge. The teams were like hundreds of people. And here we are with our, very modest size equipment. And this is one example from 2010 of the team. And these are, again, our travels. We never traveled light. And depending on where we went, Sometimes we used boats, we used airplanes, of course, and cars, etc. So now I'd like to tell you a little bit about what we discovered scientifically. It just so happens that I mentioned the iron 14, and there are other iron lines. Iron is the most abundant element, and they all emit lights in different colors or wavelengths in the corona. And each one of these colors corresponds to a different temperature. So, for example, here I'm showing you the iron 10 plus, which is iron 11, and iron 14. Their response curves or their dependence on temperature is well separated. So if you observe something in iron 13 plus and you don't see it in iron 10 plus, then you know you have gas at this temperature. So it's a very important fiducial mark for, it's almost like a thermometer you're sticking into the corona. So I showed this picture. What we have is we have this stack of cameras, and I can maybe describe them later if anybody's interested, but I'd like to move on before I lose time. This is what an example from the 2023 eclipse as we were approaching solar maximum. So we observe in white light, which are these pictures. This is depending on the focal length of the camera, you can get a very large field of view, or you can get very, very high resolution in a smaller field of view. Now, what I'd like to bring to your attention are, in addition to these beautiful white light images, is what we achieve by having filters which take out the iron 10, 11, and 14. So if I didn't tell you that this was the same eclipse, you wouldn't have guessed because they look so different. And what the difference comes from, whatever rays you are seeing here have the different temperature from the rays you're seeing here. So here we have a very complex and comprehensive map of the distribution of the temperature in the corona. It's true, it's at 1,000,000 degrees and above, but not everything is at the same temperature. And this beautiful composite is from the white light and the iron 10 and the iron 14, which is shown in green. So you can see the complexity of the corona, and it's all its glory. This is an example, a comparison from the 2024 eclipse, and also another one that was taken in 2017 when the sun was at a different phase of the solar cycle. So this shows you also how the distribution of the temperature changes in the corona, also as a function of time. Now, what's really interesting, and this we found from looking at our eclipse observations of similar to these multi-wavelength observations over a period of 15 years. And what we found, and we looked at the data that are collected in interplanetary space. So basically these iron ions that exist in the corona are picked up in interplanetary space as they have different equipment to pick them up. And it was very interesting. So this shows you a continuous observations taken in 2006 when the sun was at minimum activity, and this one in 2013 when it was at maximum activity. And what we noticed is the charge state really occupies almost a constant band in the solar wind. Around the 10 plus. And in our observations, the 10 plus is the one where you see open rays starting from the base of the corona. Whereas here, if you go to iron 14, things are more closed, they're more clustered, but in iron 10, they're different. So this was the first time that we could make a connection directly between the eclipse observations and what's observed in interplanetary space, telling us that the solar wind is originating from the sun in regions where the temperature is around 1,000,000 degrees. And these ions are preserved. They don't change their personality once they pass a certain distance in the corona. And this is what's captured in interplanetary space. And this is the first time anybody has made that connection. Now, there's another aspect to the corona that I'd like to share with you, and this is what I call the turbulent corona, because it's really you think of the corona as a gas, but it really has sometimes the same properties as fluids. So, for example, you see waves in the ocean; they're breaking into smaller and smaller waves. You see clouds that have all kinds of forms. Well, the corona presents us with very comparable things. So one of the first things that was also discovered from space is what we call coronal mass ejections. So this example here on the left is the eclipse image, and you see this huge bubble over here that was captured. And before I start this animation, so this is the artificial occulter that I mentioned before. So this is the size of the sun that's identical to this size here. So I would like you will see things moving outwards from the sun, but I'd like you to focus on this region because you will see how this captured something as it was coming, emerging from the sun. So now you start to see like a forefront of a huge bubble that's emerging from behind the occulter. And I will stop it at the point where then you see exactly this feature. Oh, sorry. Okay. So it moved the page instead. But anyway, the point I want to make is that not only are you filling the gap, but the incredible details from the eclipse images that we can acquire because we have photographic capabilities that are not available in space at the moment, especially in the visible part of the spectrum. That tells you exactly. So this big bubble here still remains tethered to the sun if you look at the eclipse image. Now, the 2024 eclipse, I also want to give you an example where you have not only these huge explosions, but you have, so this is what the corona looks like with a smaller focal length. And this is a close-up. So you can see that all this very, very close to the sun, there's an incredibly turbulent medium. And we found, I'm just going to go through examples where you see these huge waves. And this is from a spacecraft that's called Whisper that's orbiting the sun. And what they see, the same things we see in the corona, but we see a snapshot, they capture them moving away from the sun. So I'm just going to run it a little bit because I still have some material to cover. This is a huge coronal mass ejection. And this on the left is the sun, the size of the sun. Okay. Now, there are other smaller features, and we call them vortex rings, and they are a reflection of a lot of turbulent motions and instabilities that are happening in the immediate vicinity of what I call prominences. Now, I don't have time to describe everything about prominences, but I just want to give you a flavor of all these different things. On the right here is what you see captured in the Whisper data. And at the time when they discovered them, they didn't know where they originated from. So we've recently submitted a paper where we showed that all these vortex rings are actually originating in the vicinity of prominences. So this is just a video that shows you how these vortices are appearing in the Whisper data over time. Now, there's another type of instability, which is called the Kelvin-Helmholtz instability. And sometimes you will see these features. They're like wavy patterns with crests, and you see them in clouds, and they also appear in the eclipse. These are three examples of different coronal mass ejections that had their counterparts in the Whisper data. And this one shows you how they're emerging, from in space. Okay. Now, there is one thing about the prominences that is really worth while pointing out. They're very, very dynamic, and they are the most dynamic features in the corona. So if you look, you can see how all of a sudden it's exploding and spewing material into space, and some of it falls back down. In the eclipse observations, we don't have this time sequence, but we can see how this very complex structures, they connect to the corona. So when the red is in hydrogen, when it turns into gray, that means the material has become ionized because this is neutral. And this other example shows you that the prominences are always like enshrouded with the hottest material in the corona. So this is a discovery that was only possible from the eclipse observations. Now, before I want to end with just giving you a glimpse of the most ambitious eclipse expedition that I have led. This was in last year in April 2024. So we had 3 observing sites, which were, sorry, the yellow ones, just focus on the yellow ones, separated by about 1,200 kilometers. And we wanted to maximize our chances for observing. And fortunately, we did this because Kerrville was totally clouded out. Torion had a sandstorm. They managed to get some data. But luckily in SIMS, we got beautiful skies and we got really the type of observations I just showed you earlier. And we also, it was the first time I was doing a payload from the airplane. So NASA has a research aircraft called the WB-57, and we took full advantage of the space that was available. So two spectrometers were in what they call the nose bowl ahead of the cockpit, and then these 2 extrusions like enclosures that were attached to the wings called the spear pods. So we had 2 spectrometers here and imagers so this were the preparations in the lab. Excuse me, and this is the team at Johnson Space Flight Lab. So my life would not have been the same without the Solar Wind Sherpas and without the financial support from NSF and NASA. And before I want to just, for fun, there were these quotes from different observers, and this was published in a book by David Barron. And I just want to read to you what it means to witness or be prepared for a total solar eclipse. And this one is, the person says, the depth of anxiety experienced by an astronomer in the hours before a total solar eclipse are difficult to fathom. With so much to do and so much to go wrong, emotions can overwhelm. I could not help sitting down and having a good cry. And then another Harkness, the one who discovered the iron-14, he said, like, you had no time to pay attention to anything, but everybody worked as if for their lives. So you can look. And I found this cover in the book by Maunder, published in 1898. And I think this picture here really depicts the human aspect or the human experience of a total solar eclipse. So this is a Muslim who was actually, he had his prayer rug and he was witnessing the eclipse, and basically it's like almost a supernatural experience. And from a scientific point of view, the corona is actually our only window into the magnetism, which drives the dynamic behavior of plasmas in our universe. I think so. I will stop here.
Thank you so much, Shadia, for that really, really interesting talk. Some of the things that you had up there I hadn't seen in quite some time, so it's nice to get a reminder, a refresher of the things that I learned from you in the classes that you taught. So we have some questions from the folks on YouTube, and I just want to make an announcement that please put your questions in the chat in YouTube, and we will answer them live. If you are here present in the live, if you're coming back and you're watching it later, unfortunately we can't travel back in time, but please bring on your questions and we'll try to answer as many as possible while we're here with Shadia for the rest of our time today. So the first question we have asks, is the swirl shown in the eclipse sketch produced by Temple to be interpreted as representing the onset of a CME eruption?
Yes. At the time, nobody knew what a CME was. So it was only in the early 1970s that they were discovered, because they're very faint. And to find them, you need to do some kind of an image subtraction. So it just shows you the power of the human eye that he caught it in the eclipse during a total solar. Some people thought maybe he went crazy during totality and he drew this swirly thing like a tornado or something. But yes, it was the first one, at least to my knowledge and most people's knowledge. Yeah.
It's very interesting. So we have a couple other questions that are coming through, but I want to ask if you could stop sharing your screen so
Yes,
people
I
can
wasn't sure
watch
whether.
you speak.
Yes.
I have some questions. Maybe we can intersperse with the audience questions coming in my own. You said earlier that you participated in expeditions for 20 solar eclipses. I know that many of them were clouded out, as you were talking about before, but I wanted to ask you, what your favorite was and why is that? Because I've never seen the solar eclipse myself. So, or a total solar eclipse. I've seen partial ones.
Uh-huh.
And I've heard so many different things about the experience, like the whole body experience of witnessing an eclipse. But from your perspective, from an astronomer's perspective, who's there to study it, what is it like for you when you're out there experiencing an eclipse? And what was your favorite one that you've experienced thus far?
Okay, my first one in India in 95 was the first experience, and it was really, I mean, it's very, very hard to describe. It was surreal. It was early in the morning, and it was the phase of the solar cycle was at solar minimum. So this is when you see long elongated streamers going away from the sun. And I could swear I heard this when it's all of a sudden the corona appeared and these streamers were darting into almost infinity. So that's the first one. My other favorite was in Libya in 2006. We were in the Sahara, in the southern part of Libya at the border with Chad. And it was my favorite from many, many different points of view. First of all, the desert was incredibly gorgeous. The hospitality of the Libyan people was incredible. And also, it was for many, many years, I was trying to capture the what we call iron Roman numeral 11 line. Nobody had imaged the corona in that line because it's at the border between the optical and the near infrared. So the last 40 seconds of the eclipse, my postdoc at the time managed to capture it. And it opened the floodgates for our research because then it took me 6 months to realize why we saw the light, the emission going so far from the sun. And and that's what really led us to develop other diagnostics, to probe into the physics of the corona, the discovery of the iron 11 line. So from many points of view, I mean, it's a unique experience for me. I mean, I come from Syria. It was an Arabic country, and it was just the the people. When they see you speak their language, it's a different relationship. And so, from a human point of view, it was extraordinary, and also from a scientific point of view.
That sounds fantastic. Next time you go on an expedition, if you need an extra set of hands, just let me know. Um, so we have one question here that I unfortunately don't have all of the context for, but they ask, Physica asks, does this explain the pink streak seen in the eclipse of April 2024? Unfortunately, I don't know what this refers to, but maybe you have some more
The
context for
pink
what that means.
streaks is probably there was a very, very large prominence at the south. Because I wasn't usually I'm running experiments and I don't have time to look. I can't remember many eclipses. But in 2024, I had a group of young people who had not automated, but things were much more, streamlined than before. And I was able to observe the whole eclipse. It was striking because there was a huge, what they call the prominence, the pink streak, at if you look at the clock, it's around 5 o'clock in the sky. So that was, uh, a huge prominence that I don't know if they wanted what explains the pink streak. I'm not sure what they mean by what I need to explain. Mhm.
Well, maybe can you explain what the pink streak is?
So the prominences, why they're very intriguing. I told you that the corona is at over 1 million degrees. The prominences vary between 10 and 50,000 degrees. They're very dense, but they're very cool. And it's like putting an ice cube in an oven and it stays intact. So it's very, very strange. But they're so dynamic. Even you can see them. They're so bright that if you have one of these special telescopes with a filter called a coronado, you can look at the sun on any day and you see them like flickering and jumping around and they just explode. So their dynamics is really, in my opinion, is what drives all the dynamics of the corona. You have all the because of this thermal instability between a very cool and dense material with the surrounding hot and tenuous one, they can't stay stable and they just everything around them becomes very unstable. And they also drive the coronal mass ejections when they explode, as I showed you in the movie that was made with the Solar Dynamic Observatory in the extreme ultraviolet. So I didn't used to pay much attention to them because I thought, okay, they're just these cool things. But for the past 10 years, I have come to realize that they are really uh, playing a fundamental role in the dynamics of the corona and also linking to the magnetic field that's emerging from the solar surface.
Amazing. So actually, Physica has another question. So are there plans to follow the Spain and Egypt eclipse with the plane and the equipment that you described from your last experience?
Yes. The answer is yes for the ground and no for the plane, unfortunately, because I did submit a proposal to NASA to use the plane again and it was turned down.
It's a shame.
Yes.
Did they say why it was turned down?
Well, I
Not
think it's
novel enough anymore?
all the funding situation in the US
Ah,
at the moment is what
yes.
was.
Okay. Understood. Um,
So we have to do a GoFundMe
yeah, I think
campaign.
you'd get a lot of support for that.
Yeah.
So I want to ask you a question in maybe the next couple minutes of our time together. I mentioned at the beginning of this that you were one of my mentors, someone that I really looked up to and still do
Yeah.
during my academic career, my career as a communicator. And I want to ask you about the mentors that you've had and how they've kind of shaped your experience as a scientist, as someone who's been a real pioneer in this arena of astrophysics.
Okay, so I actually never had a mentor. I was at the time when I was going through my graduate school and postgraduate and so on. There were very, very few women. I was the only one in. I was in a physics program. I never had astronomy like a. Uh, I didn't go through an astronomy program. I went through a physics program, and the first time so when I finished my PhD, I was applying to different programs for a postdoc. And I told my advisor as I was applying to this special program for postdocs at the National Center for Atmospheric Research in Boulder. He said, well, uh, you're wasting your time. None of my students ever got in. And I actually was accepted, and he couldn't believe it. And what he told me was, he said, I didn't tell you I was a male chauvinist pig, but you changed my mind. So, so that was, but then I went to Boulder and I worked with two scientists, and uh, this was my entrance into solar physics, and they were fantastic. I had maybe one of the most successful years in my career as far as, getting into a new field. Um, but their mentorship stopped. It was just that one year. And when I went afterwards to Harvard, I was more or less on my own. So it went back to being by myself. And I just would do things. I think it was to my advantage because I came into a field without any preconceived ideas. So I was free to discover things. And that's what I try to encourage students is that don't go by the prevailing view, your observations. I mean, I was a theorist, but then when I started to do observations, The data are telling you something. You don't have to try to fit a theory into your data. You look at the data and you say, what are they trying to tell me? And this is what I try to encourage students to do, because many times I see it all the time, scientists are stuck in, oh, this is what the way the corona looks like. You have at solar minimum, you have all these regions where have all open rays, and this is where the fast solar wind comes from. And then after working with the eclipse observations, it's just not true. The solar wind is coming from all over the surface of the sun. And it's so difficult to change the opinion of people, even to this day. Very few want to change because it's uncomfortable for them. It has led them to all their models are driven by this kind of view, and it just doesn't give you the right answer, but they keep on wanting to do the same thing.
Yeah, it can be difficult to let go of something that you've held on to so tightly for such a long time.
Yes. So to answer your question, I mean, my experience wasn't ideal, but maybe in hindsight, I feel like it forced me to be an independent thinker, to have the courage to forge ahead. And I always felt like I was walking a tightrope. The funding was always an issue. But I was fortunate, I mean, to be able to survive in such an environment. When the students ask me about my experience, I tell them, well, I don't wish it on you because it wasn't ideal, but at the end of the day, I managed.
You did indeed. And boy, did you ever manage.
Uh-huh.
So we have time for one more question. I'm gonna take the question from Edgar, who says, in Guatemala, during the
Mhm.
1991 total solar eclipse, in the previous moment, maybe the last moment, we watched dark and bright bands running on the ground, and we didn't have an explanation for this phenomenon.
Mhm.
Uh, can you explain? Do you have an explanation for that, maybe?
I don't. I have never seen them. Unfortunately, I've never seen them, but it's a very, very strange phenomenon. I haven't found an explanation for these ripples.
Can
It's
you
very,
can
but I
you
know
can you explain what they are, maybe, for
they
people who
look
have?
like you look on the surface on the ground and you see like black and white stripes and just it's almost like you have a wave that's floating, but it's not tangible. I mean, it's just light that's kind of vibrating across the surface. It doesn't last very long. It's very short. But given that I've always been busy with the equipment, you just have to be not busy and just look around you and then you see them. But I have never witnessed them.
Have you ever had the ability to just, let all of your team worry about the equipment for the eclipse and just like experience it yourself?
Yes, 2024, last year.
Yeah, yeah,
That's the
that's
first
great.
time.
That's great. Well, I'm glad you had that experience.
Yeah.
Because it's such a
I
amazing
mean, I
thing.
didn't mention about another unique experience in 2023 where we decided to fly a spectrometer with a kite. And that was a thrilling experience for sure. So we managed to get data. The kite was swinging, but in the swinging motion, the spectrometer passed by the sun, and we got spectra. So we published the paper, and the referee said this was the most fun paper he had ever read.
That's wonderful.
Yeah.
Um, we have a few other questions. I think I'm gonna go with the last one that just came in from Miriam, who asks, could you please give us advice in the Arabic language? I'm sure what advice about, but maybe you can make that decision on your own.
Okay. Um, let me think just a second. I have to switch keys. Um, الحقيقة إنه الواحد أهم شيء إنه يكون عنده ثقة بنفسه وما يخاف إنه يجرب شغلات جديدة بحياته. I said
So this is
the
actually,
most important thing is for people to have confidence in themselves, not to be afraid to try something.
that's wonderful. That's wonderful advice for everybody in every language.
Yes,
Um,
exactly. Exactly.
so this is, I mean, I would love to be able to talk with you more about eclipses and
Yeah.
being a woman in science and
Mhm.
uh, having to kind of code switch between thinking in English and thinking in Arabic.
Yes.
But we're unfortunately out of time for today. So I want to
Mhm.
thank you again for your time and all of the work that you've done throughout your career and what you will be doing in the future. And thank you again for being here with us.
Oh, well, thank you
Um,
so much for inviting me. It has been a pleasure to be able to share my experiences. Thank you, Kelly.
Wonderful.
Yeah.
Yeah. Okay. Well, thank you so much. Thank you to everybody who joined in live. And we'll hopefully see you again in the September edition of our Women in Solar Physics webinar series at the Office for Astronomy Outreach.